Hey everybody, today we're going to talk about fractional exponents. But before we do that, let's review the basic idea of positive whole number exponents, because that's going to help us kind of motivate our new definition for fractional exponents. Now, that basic idea is repeated multiplication. That's kind of how you think of exponentiation when it's first shown to you. For example, 3 to the 5th power is equal to 3 times itself 5 times. So 3 times 3 times 3 times 3 times 3. This will happen 5 times. And in general, if you take some number x, the base, and raise it to some whole number y, you can think of this as x times itself y times. So in this specific example up here, y was 5 and x, and x was 3, and we were multiplying 3 by itself 5 times. And this notion of exponentiation naturally leads to a sort of pattern, and that is, if you exponentiate something once, then exponentiate again, you multiply the exponents. For example, 3 to the 5th power, then to the 2nd power, is first taking 3 to the 5th power, or 3 times itself 5 times, and then taking all of that and doing that so 3 to the 5th again, or 3 times itself 5 times again. Now notice that this is equal to 3 times itself 10 times, right? We're multiplying by 5 times here, and then we got 5 more times here. And so that's equal to 3 to the power of 10, which, coincidentally, is 2 times 5. And this is true in general. If we take any base we want, we'll call it x, first raise it to one exponent, that's a positive whole number, and another exponent that's a positive whole number. We first multiply x by itself e1 times, so the first exponent, and then take that thing and multiply it by itself e2 times, or the second exponent, for a total of e1 times e2 multiplications of the original base, which is the same thing as raising the original base to e1 times e2. It's this pattern that we're going to use to extend the definition of exponentiation past positive whole numbers. And we're going to start with fractions. Now, let's say we're trying to do this for a specific number. Let's say we're trying to decide how to extend this definition of exponentiation. We want to decide what to define 3 to the 1/2 as, right? We want to set this to some number that makes sense in some way, but we don't know what that is yet, so we'll just kind of leave it there as its own unit for now. However, we know that no matter what we kind of decide that this equals, it should equal something that preserves this old pattern of multiplying exponents. So we're going to take our expression here, 3 to the 1/2, and square it, or raise it to the 2nd power. And according to that pattern that we want to preserve, this should equal 3 to the 1/2 times 2, which is 3 to the 1, which is 3 just by itself, or 3 multiplied by itself one time. Now that means that this thing here is the thing that you can square to get 3, which by definition is the square root of 3. That means that the square root of 3 is the value that we should be assigning to this expression 3 to the 1/2 in order to preserve that old pattern that we want to still hold. By similar logic, if we want to assign some value to, let's say, 3 to the 1/3, well, we know that cubing this thing will give you 3 to the power of 1/3 times 3, using that pattern that we want to preserve, which again equals 3 to the 1, which is just 3. And so 3 to the 1/3 is the thing that you can cube to get 3, which again, by definition, is the cube root of 3. Now, this logic works for any base and any whole number denominator, and that lets us, in general, assign a value to all expressions that look like x to the power of 1 over y, and it lets us do that in a way that makes sense. So we'll have this equal, as we've done so far, the y-th root of x, which we often write as x with the radical symbol and a little y on top of it. And again, this is the thing that you can raise to the y-th power to get x. So x, y-th root of x, to the power of y, gives you back x. Now once we have this, we can assign values to any fractional exponent using this same pattern. For example, 3 to the, 2/5 is equal to 3 to the 2 times 1/5, which is equal to 3 squared to the 1/5, which equals 9 to the 1/5, or the 5th root of 9. And in general, if we take some base and raise it to the power of some fraction, we'll call it z over y. This is equal to x to the power of z times 1 over y, which equals x to the z, whatever that turns out to be, all to the power of 1 over y, or the y-th root of x to the z. Anyway, I hope this way of generalizing exponents makes sense. That's all I have for today, and see you all next time.